Hello there. And in this video we're going to discuss the idea of how to algebraically determine whether a given curve has symmetry, but not just any symmetry, namely axis and origin symmetry. So let me graphically demonstrate what I mean. So consider some curve, for example, y is equal to x squared. So y is equal to x squared, assuming that I know how to graph appropriately, should be symmetric about the y-axis. So when I say symmetric about the y-axis, pretty much this side of the curve is a mirror image of the left side of the curve. So this is what I call having y-axis symmetry. If a curve has x-axis symmetry, then it should be symmetric about the x-axis. So when I say that, that means the top of this side should be a mirror image of the bottom side. And if I say that a function has origin symmetry, I imply that a curve pretty much has this type of symmetry, where this graph is the same as this graph. So it's pretty much a reflection across the x-axis and also the y-axis. So in this video, we'll discuss how to verify whether a particular curve has symmetry. So let us begin to formulate how we can algebraically test whether a function has a particular type of symmetry. So let us first consider y-axis symmetry. So y-axis symmetry is going to have the following type of behavior. So let us assume we have something like this, like an M. So this is definitely going to be symmetric about the y-axis. So how can we sort of test this algebraically? So let us pick any point A, and let us just pick its negative point on the other side of the origin. So these lengths have the same exact distance. So if this is truly symmetric about the y-axis, then the heights corresponding to symmetric x values should have the corresponding same y values. So we can look at the parabola again as we did in the introduction. So if we pick a point, say A, and we consider its point negative A and consider the y values, then those points should meet up on a horizontal line. So this is what we consider curves that have y-axis symmetry. So if we give these curves names such as f, then we can see that f of A is going to be equal to f of negative A. And this has to be for all A inside of the domain of the relation. We're going to be primarily focusing on functions because that's typically what we discuss in the early mathematical courses. So this is what we refer to as the definition of a y-axis symmetric function, which sometimes people refer to as an even function. So a function is even if it is symmetric about the y-axis, and you can prove that a function is even via plugging in negative a for any a in the domain and seeing if it equals the same value as f of a. So let us consider the origin symmetry. So origin symmetry. So similar to being symmetric about the y-axis being called even, if a function is symmetric about the origin, we call this function an odd function. So let us consider the graph of a function that is symmetric about the origin. So consider something like this. So this would be maybe like a cube root curve or something similar. So if this is truly symmetric about the origin, and we pick a point A, and it has some corresponding value, f of A, and we pick another value, say negative a, and we look at its value, which is going to be negative f of a, or f of negative a. Oh no, where'd my graph go? There he is. So there's a y, there's an x. Let's see. So this is going to be f of negative a. So if this is truly symmetric about the origin, then this distance here and this distance here should be the same. So this implies that f of negative a must be equal to the opposite of f of a, if it truly is an odd function, which is the same thing as testing whether it has origin symmetry or not. So what about a curve that has x-axis symmetry? So if a curve has x-axis symmetry, that means it has to look something like this. So if this is the case, clearly this is not a function of x. You can easily test that by drawing a vertical line, and it's going to fail the vertical line test. Actually, the only curve that is symmetric about the x-axis that is a function of x is the curve y is equal to 0, namely the x-axis. So is there still a algebraic relationship that we can sort of plug in here to sort of see that it is symmetric about the x-axis? Yes. So if we pick a point A, so this is going to correspond to some y value, say b, and then this is also going to have some value. This should be equal to negative b. So if we sort of flip this curve on its side, so now this is going to be the y-axis and this is going to be the x-axis, and we can call this relation g. So here we're picking this point here, b, and this point negative b, and here's the a value for which supposedly they should be equal to each other. If it truly is symmetric, then we can see that g of b is going to be equal to the same as g of negative b, where g is a function of y. So we say g of y is equal to x. So that is how to test whether a relation is symmetric about the x-axis. But if it's symmetric about the x-axis and not y is equal to 0, then it's not a function. So we typically do not consider this case. So let's look at a couple examples. So example 1. Suppose f of x is equal to 3x squared or 3x cubed minus 2x. So a question you may be presented with is this function even? Is this function odd? Or is it neither even or odd? So when I say even, I'm talking about y-axis symmetric. If it's talking about odd, I'm talking about origin symmetry. And neither means it's not symmetric about the origin or the y-axis. And it can't be a function of x if it is symmetric about the x-axis. And it's not equal to 0. All right, so how do we test this? So we're going to plug in negative x and see what type of relationship it has to f of x. Because if it is even, then that means f of negative x is going to be equal to f of x. And if it's odd, so this is even, so if it's odd, then f of negative x is going to be the opposite of f of x. So let's see what happens. Let's change color. So let's see, what color? Let's go red. So f of negative x, so let's plug negative x in everywhere we see x here. So we have 3 negative x, the quantity cubed, minus 2 times the quantity negative x. So when we have a negative number cubed, it still becomes negative, so we can rewrite this as negative 3x cubed. And we have negative 2 times negative x, so that's going to be positive 2x. So we're going to factor out a negative sign here, so I'm going to pull out a negative sign here. So 3x cubed becomes positive and 2x becomes negative. But this thing inside brackets is precisely the definition of f of x, so this is going to be equal to negative f of x. So we've proven that for some arbitrary value x, f of negative x is equal to negative f of x. So this implies that f is an odd function, which means that f is symmetric about the origin. So let's do another example. Suppose we have h of x is equal to 5x squared minus 2 over 7x to the fifth plus 3x. We're going to begin by doing the same exact thing. So we're going to plug in negative x and see what happens. So this is going to be equal to 5 times negative x, the quantity squared, minus 2 over 7 times negative x to the fifth plus 3 times negative x. So when we square a negative number, it becomes positive. So the top of this is just going to be 5x squared minus 2. When we raise negative 1 to an odd power, it becomes negative, so we have negative 7x to the fifth. When we have 3 times a negative number, that becomes negative, so we have negative 3x. So I can't really do anything to the top, so I have 5x squared minus 2. I have a couple negative signs, so I can factor out a negative 1 out of the bottom, leaving me with 7x to the fifth plus 3x. So we have 1 divided by negative 1. We can just write that as negative 1. So we have negative 5x squared minus 2 all over 7x to the fifth plus 3x. But this expression here is precisely the definition of h. So we have that this is negative h of x, and this came from the expression h of negative x. So since h of negative x is equal to negative h of x for all x in the domain of h, we have that h is odd, or symmetric about the origin. So let's look at another example. So suppose we have k of x is equal to x squared plus 2x plus 1. So I'm going to plug in negative x again. So k of negative x is equal to negative x the quantity squared plus 2 times negative x plus 1. So when we square negative, it becomes positive, so we have x squared. And then 2 times negative x is going to be minus 2x, and then plus 1. So is this the same thing as the original, or is this the same exact thing as the opposite? So negative x squared minus 2x minus 1. So what do we have here? So this is k of negative x. So can we rewrite this algebraically somehow that sort of relates to the original? So this is maybe optional, depends on how comfortable you are with these types of things. So how can we write negative 2x in terms of 2x? So negative 2x is going to be the same as positive 2x minus 4x. So that will give us negative 2x. And we have this plus 1 out here, so we can just leave that there. So what do we have here? Well, we know that x squared plus 2x plus 1, x squared plus 2x plus 1, is precisely the definition of kx, and we have this negative 4x out here. So we have that k of negative x is the same as k of x minus 4x. So we see that k of negative x is not equal to negative k of x, because, I mean, maybe sometimes it's true, maybe not. It depends on the values of k, because we have this negative 4x term that's hanging outside. We also have that k of negative x is not necessarily equal to k of x. Now, this possibly is sometimes true with this identity, depends on the values of k, but it's not necessarily true because, again, we have this negative 4x term outside. So based on all of these observations, we see that it's not necessarily even or odd. So since by definition of symmetry groups, then odd means it's always symmetric by the origin, and even always means it's always symmetric by the y-axis. So you can't have both, and you can't have part. So it's always symmetric or always not symmetric. And what I mean by that, so suppose we have like, it's symmetric here, but it does some other things, that's not really symmetric. So that's what I mean by sometimes symmetric, sometimes not. So this is not what we call a symmetric by the y-axis function, because it's not true for every value in the domain. It can't be, some it works and some it does not. So in this case, we say that this is neither odd nor even. And that is just some basic algebraic tricks that you can use to verify whether a function is even or odd, which means a function is either symmetric about the y-axis or symmetric about the origin. And remember, a function cannot be symmetric about the x-axis unless it is precisely the x-axis or a subset of it.